Okay, so this is a quick video about adiabatic work. Adiabatic means that there's no heat that can enter or leave the system. That means your system might be insulated, for example. Before I made this video, I was curious about where the word adiabatic came from, and so I looked it up. Adiabatic means impassable, from the Greek, impassable, which I thought was kind of amusing. And then I thought about it in a different way, and I thought maybe it was less amusing, so please do your homework. Okay, so how do we find work from an adiabatic process? So Q equals 0. There's no heat. That's what adiabatic means. And if you want to find the work, well, you do what you always do, which is you know where you start in terms of the volume, you know where you end, and you integrate PDV. The problem is we have absolutely no idea what the pressure is. So we can't integrate this. We're not given any information about how the pressure changes. So we have to figure something else out. So you say, oh, aha, I know what we'll do. We will use the first law of thermodynamics, and we know that, look, heat is 0. And so, oh, this is easy. All we got to do is write down the energy for an ideal gas, which we know from kinetic theory, and we set that equal to the work. That's great. The problem is you don't know the change in temperature either. Even if you're given the initial temperature of the system, you don't know how the temperature and pressure evolve. And so that means that this approach is not going to work any more than this approach is because you don't know the temperature. So you need a new approach, okay? So what we're going to do is we are going to use the first law of thermodynamics in a slightly different way. I'm going to write it the same way, but this time using differentials. And you might say, well, how is that going to change the physics of it? I get it that we do calc or something, but it actually does change the physics. When I write delta U equals Q minus W, what I'm saying is at the beginning and end of a process, the heat that is added minus the work the gas does, that is balanced. When I put it in differential form, it makes a different statement about the universe. It says that the instantaneous change, in other words, moment to moment, the heat and the work have to add up to the change in energy. In other words, it can't just be the case that at the beginning and end of a process, the energy is balanced. It has to be balanced at every single second instant during which the process has taken place, which is actually a much stronger statement than the original statement that it has to be the same at the beginning and the end. In other words, there's no borrowing energy and paying it back later. It has to be balanced all the time. Okay, so what does that buy us in terms of calculation? We can still say dq is 0. We're going to write basically the same thing we did last time, only with dt's instead of deltas, but let's take it a step further this time and get rid of that P in favor of nRT over V. This is you just using ideal gas law. So if you look at this, you've got a dV and a dt, but you've also got some other stuff. And if you remember from calc, if you can get all the variables of one kind on one side, so if you get all the t's on one side and all the v's on the other, then it's separable and you can integrate. And that's easy. You just divide by t. This thing was built to be integrated, and so let's integrate it. We know initial temperature, final temperature, initial volume, final volume, and when you integrate, you end up with something that looks like this. So you do a little bit of algebra and you end up with this relationship. Aha. This is a very good relationship. It means that if you know the initial volume and the initial temperature, that's related to the final volume and the final temperature. So just to expand on that a little bit, we just derived that by doing a couple of integrals. And the important thing is now we know what the final temperature is. We know what the final temperature is, and so we can go back to our idea in the first place of saying that the work is minus the change in energy, which is this. Only now we know delta T. Great. On the other hand, you might say, well, look, I don't want to do things in terms of temperature. I'm more comfortable putting things in terms of pressure and volume. I don't know why, but let's just say you are that way. And that's reasonable because work has to do with pressure and volume. Fine. Let's take this above equation and use the ideal gas law to get rid of T. And now you have something that looks like this. This is just another way of writing that same statement. Now we can come back to our work and write it in terms of pressures and volumes by substituting this out via the ideal gas law. And if we do a little bit of algebra, holy Toledo, look at how simple this is. I'm glad we wrote it this way because look, it's just P1V1 minus P2V2. That is easy. It's easy, easy, easy. And so if you know the initial pressure and volume of a system and you know the final volume, you can find the final pressure using this and then calculate the work. Okay? So to sum up, if you have an adiabatic process, there's one of two things you can do. You can either use this and figure out the final pressure or volume or whatever using that, or you can use this and figure out the final temperature or volume using the second one. Okay, hopefully this was more helpful than confusing.